All right, so I wanted to work through the second exam and show you how to do all the problems. So I guess let's get started. So first one is a limit. So remember, you want to make sure that bad behavior is possible before you start trying anything tricky. And so like if you try plugging in, you're going to get 0 over 0, of course, which remember, we don't know anything about. Probably back from Calc 2, you learned about L'Hopital's rule and indeterminate forms. There's no such thing as a multivariable version of L'Hopital's rule, so we won't really be ever using that, but hopefully you do remember that 0 over 0 could be anything. We don't know. Okay, and then so I guess we could try along y equals mx to see if this value that f approaches depends on m. If it depends on m, then it depends on which path we take. And if it depends on which path we take, then the limit doesn't exist. Because remember, the whole idea of the 2D limit existing is that no matter how you approach the origin, no matter what line, no matter what parabola, no matter any curve you take to get to 0, 0, it should give you the same thing. So anyway, along y equals mx, we'll get the limit is x goes to 0 of 3 times, I guess this is going to be mx cubed minus m squared x cubed over x cubed minus 2m cubed x cubed. And so notice that there's a factor of x cubed on absolutely everything. So the numerator, after we cancel out an x cubed, is going to be 3 times m minus m squared over 1 minus 2m cubed. And so now that there's no more x's, the limit as x goes to 0 ends up just being this 3 times m minus m squared over 1 minus 2m cubed, which depends on m. And like we said a few minutes ago, if it depends on m, then it depends on the path you take. If it depends on the path you take, then the limit does not exist. Okay, so then let's take a look at this other limit question. Again, let's try plugging in first to make sure that bad behavior might be possible. And so yes, again, if, remember, cosine of pi over 2 is 0, so we have 0 minus 0 in the numerator over 0 plus 0 in the denominator, so it's still 0 over 0. And so if you tried doing lines to that point, you'll keep getting the same thing. What we were hoping for you to recognize here is that this numerator looks like a difference of 2 squares. So this is x squared minus cosine y times x squared plus cosine y in the numerator. And of course, x squared plus cosine y is what we have in the denominator, so that cancels, and so we get the limit of x squared minus cosine y. And then that we can plug in 0 pi over 2 to get 0. So it's just like something you would have had in Calc 1, you know, if we were doing the limit as x goes to 0 of something like x squared over x, right? You could cancel out a factor of x to get something that actually makes sense. And so, yeah, looks like the limit is 0. So for a limit to exist, you can't make any reference to actual paths. Whatever you're doing, I guess we've called it algebra tricks, needs to be valid no matter what way we're approaching the given point. And so look out for things like differences to squares or perfect squares or other kinds of factoring, but we're not going to make it too crazy or too hard to see. So be on the lookout for things like that. Okay, so that one, the limit is 0. Consider the surface given by x squared plus z squared e to the x over y equals 0. So this one is it's meant to be an implicit differentiation problem. You know, if you want to find the derivative of z with respect to x, if the equation is such that you can easily solve for z in terms of x, then you can figure that out. Otherwise, you can use implicit differentiation. So that's sort of what we had in mind for this. So if you remember, when you have a level surface of the form f of x, y, z equals k, the implicit derivative formula for del z del x is minus the x partial of f over the z partial of f. And yeah, there's a similar one for derivative of z with respect to y, but we don't ask for that in this question. So anyway, it looks like the x partial of this is z plus, we have to use the, oh, okay, so then the derivative with respect to x is going to be z plus z squared e to the x over y times 1 over y. And then fz is going to be x plus 2z e to the x over y. And so then putting it together, minus fx over fz. So this looks close, but it looks like that doesn't have the negative sign. So be careful, make sure you have all the little details for things like this. You should look at all the choices, identify which ones are very close to each other, and then confirm that all the little details are correct. So that looks like that. All right. Calculate the tangent plane for the function x squared plus y to the fourth at the point 1, 1, 2. So basically we're doing like the linear approximation. Sorry about this little extra z equals. So anyway, this is what we talked about in section 14.4. So tangent plane to z equals f of xy is z equals f at the point plus the x partial at the point times x minus a plus the y partial at that point times y minus b. So it looks like the x partial is 2x. The x partial at 1, 1 is 2. The y partial is 4y cubed. The y partial at 1, 1 is 4. And then f at 1, 1, we already tell you, is 2. So we should have z equals 2 plus 2 times x minus 1 plus 4 times y minus 1. And so what? Minus 2 minus 4 is minus 6. Plus 2 is minus 4. So you end up getting that. So a lot of people put this one. And this is really, really bad. Because remember what plane equations looked like back in chapter 12. We've been dealing with them all semester. And remember, for plane equations, you don't have things like x squared or y to the fourth. So that's sort of the standard calculus mistake, is a lot of times people forget to plug in these numbers to get equations that represent either tangent lines or tangent planes or anything like that. That don't fall into that trap. Make sure you're getting something that you can recognize as a plane equation. So as soon as you see this question, you're like, wait a second, both those are complete and total nonsense. And then finally, the last thing you can always do is, the tangent plane has to include the point. So if you just forget about this whole tangent plane idea and just say, like, look, I'm looking for a plane equation that contains that point, the only answer that satisfies that is the correct answer in this case. It's not always going to be like that, but at least for this one, it turned out that if you just looked for a plane equation with this point, there was only one possibility. So be very, very careful with things like that. Okay, so then linear approximation is pretty much the same idea as the tangent plane. The idea is that for xy close to AB, a 0th order approximation would be that f of xy is pretty much f of AB, but then we can correct that with first derivative effects. So we could add in the x partial times x minus a plus the y partial times y minus b. And so the idea is that you're supposed to look at this point here, that this is near the point 1 minus 2, right? 0.99 is pretty much 1, minus 2.02 is pretty much negative 2. Okay, and then so what do we have to figure out? We have to figure out that f of 1 minus 2 is what? 3, minus 4 is negative 1, plus 2 is 1. The x partial is 6x plus 2. The x partial at minus 1, 2. is -4. The y partial is -2y. The y partial at -1, oh, and I'm screwing this. Yeah, sorry. X is +1, y is -2. So fix that. The x partial at 1 minus 2 is 8. And then the y partial at 1 minus 2 is 4. So f of 0.99 minus 2.02 is approximately, well, f of 1 minus 2 is 1 plus 8. So you could think about this as delta x and delta y. So just say to yourself, okay, how much has x changed? Well, x has decreased by 0.01, and then y has decreased by 0.02, whatever. Plug it in. It's up to you however you get this. So 1 minus 0.08 minus 0.08 is 0.84. All right. So intuitively, I think I remember looking at this and seeing a bunch of people got this as the answer. So I don't know what you did as far as goofing things up. But you should be able to rule out that just by kind of looking at this, that 3x squared plus 2x, if I decrease the value of x, I'm going to get a smaller value. And then similarly, minus 2.02 squared is greater than minus 2 squared. So you're subtracting a bigger number. So both these x and y effects serve to make it smaller. And that's what's manifested by these negative signs down there. So, if your partial derivatives have mixed signs, for example, if one was positive, one was negative, you'd have to take into account their size as well as how far you're adjusting x and y. But for this function, it turns out that near the point -1, 2, it's an increasing function with respect to both x and y. And so when we decrease both x and y, we're going to get a smaller value. So I should expect a number less than 1 is my answer. All right, but anyway, if you're working with the right formula, doing everything right, that you don't even have to worry about stuff like that. Okay, so chain rule question. So it looks like V depends on x and y, and x and y depend on s and t. So this, I guess you could think of as case 2. So derivative of v with respect to x is v with respect to x times x with respect to x plus v with respect to y times y with respect to s. Okay, so we need subderivatives. The x partial of v is 2x sine y minus 1 plus y over xy times y. Be careful with the chain rule. So that's our x partial. The y partial is x squared cosine of y minus 1. And then we have to use the product rule. So plus natural log xy plus y over xy times x. I guess what else do I have? I have the s partial of x is 1, and the y partial of, with respect to s, is t. Okay, so now we have to plug in our numbers. So when s and t are 0, 1, that's what we're going to do to plug in here. So when t is 1, y sub s is 1. But then we have to also figure out the values of x and y. So we want to plug in s and t to the to the x and y equations. So when s and t are 0, 1, it looks like x is 2 and y is 1. So when you plug in x is 2, y is 1, you're going to get, I guess, a half as your x partial, and you're going to get, if x is 2, y is 1, you're going to get 4 plus natural log 2 plus 1. So 5 plus natural log 2. And so putting it all together, the x partial v was a half. The x partial with respect to s was 1, plus the v partial with respect to y was this 5 plus natural log 2, and then the y partial with respect to s was 1. So looks like we get 5.5 or 11 halves plus the natural log of 2. All right. Next one, find the directional derivative at some point in the direction of the vector 2, 1. So remember, directional derivative, you're taking the dot product of the gradient vector with a unit vector. So anyway, the gradient looks like it is y squared e to the xy plus x squared times the x partial of the inside, which is y plus 2x. And then for the y partial, we actually need the product rule. So we're going to have 2y e to the xy plus x squared plus y squared e to the xy plus x squared times the derivative of the inside with respect to x. No, I'm sorry, with respect to y is x. So gradient at the point 2, 1 ends up being, well, y is 1, so we have 1. And then over here, that's 5. And then what? When x is 2 and y is 1, looks like we get e to the 6th. So 5 e to the 6th, and then x is 2, y is 1, looks like we get 4 e to the 6th. So just plug in, not so bad. And then we're going to do 5 e to the 6th, 4 e to the 6th, dotted with a unit vector in the direction of minus 2, 1. So be careful, you have to normalize the vector minus 2, 1, otherwise the units of the directional derivative don't work out properly. And so you do this dot product and you get a scalar. So what, minus 10 plus 4 is minus 6 e to the 6th over square root of 5. And so there we go. So common mistakes here. Don't leave it as a vector. That's what we call the half-ass dot product. And then don't forget to normalize the vector you are using for the direction. So I think this choice here is what happens if you normalize the gradient instead. That gives you a different answer. So make sure you don't divide by the length of the wrong vector. And then maximum rate of change, remember that really is just the length of the gradient, which is the length of 5 e to the 6th, 4 e to the 6th, so what, 25 e to the 12th plus 16 e to the 12th, which is e to the 6th times the square root of 41. And then the direction of maximum increase is really just the gradient. So remember, the meaning of the gradient is it's a vector quantity, so it has both direction and length. The direction of the gradient tells you the direction in which your function increases the fastest, or the most uphill direction. And then the length of the gradient represents the rate of change in that direction. So these these last two questions here, pretty straightforward, just length of gradient and gradient. All right, tangent plane for this situation. So again, it's supposed to be a plane. So you should immediately be able to rule out these equations here that aren't equations of planes. Remember, planes are ax plus by plus cz equals d. You don't have anything like y times z or z squareds or any of that nonsense. So really immediately throw those out. And so whereas we had the tangent plane to the graph back in this previous question, so graph, remember, was when you have z equals f of xy, for this one, this is a level surface. So this is written in the form big F of xyz equals 23. And so you're going to use the regular plane equation with normal vector given by the gradient at whatever point we're talking about, and then the given point. So it looks like the gradient here is 2xy, x squared plus 2yz, and then y squared plus 2z. The gradient at 3, 2, 1 is, well, 6. No, I'm sorry, 12. 2 times 3 times 2 is 12. And then 9 plus 4 is 13. And then y squared plus 2z is, what, 4 plus 2 is 6. So I use the normal vector 12, 13, 6, and the point 3, 2, 1, and it looks like this. So again, you know, we're not guaranteed to do this. And it turns out it doesn't narrow you down to the exact correct answer, but we want our tangent plane to have the point 3, 2, 1. And so I think I saw that this was a common mistake. People sort of thought this 23 was important. It ends up not being. But if you tried 3, 2, 1, you would get 0 equals 23. So that point isn't on this choice. So that choice is clearly bad. So again, like if you're ever afraid of missing small little tiny details for this type of thing, just check, you know, is the given point on the plane? And hopefully that helps you narrow things down. So yeah, the point is actually on this one as well. This one, this choice was sort of familiar to the other situation from a few problems ago. We were making sure you understand the difference between z equals f of xy situation and f of xy z equals k situation, that they're slightly different in how you approach them. All right, so let's keep going. Finding and classifying critical points. So, okay, to find, remember we set, so that's, you can't tell from these drop downs, but the choices are like local min, local max, saddle, all that fun stuff. So we're setting the partial derivatives to 0. So we get that fx is 2y minus y squared minus x squared. And then the y partial is 2x minus 2xy. And whenever we're looking for critical points, we need both partial derivatives to be 0. So the way I like to do this then is deal with the simpler equation first. So this second equation is telling me that 2x times 1 minus y equals 0. So it's telling me that x has to be 0 or y has to be 1. And then if x is 0, the first equation is telling me that 2y minus y squared is 0. So y times 2 minus y is 0, so I get y is 0 or 2. And then if y is 1, the first equation is telling me that plus 1 minus x squared is 0, so x is plus minus 1. So we have the critical point 0, 0, 0, 2, 1, 1, and minus 1, 1. And so be careful. I remember I suggested staying organized like this because you don't want to mix and match. That you might be tempted to think that 0, 1 is a critical point. Sure, 0, 1 makes the second equation 0. But if you try 0, 1, if y is 1, x is 0, you don't get the first equation to work out. So if you stay organized, it should take care of itself. But be careful. So 0, 1 is not a critical point. And neither is 1, 2. So just plug in to both partial derivatives, see if they're both 0, and no, they're not. Okay, so as far as classifying these go, remember we're doing d of xy is the x second partial times the y second partial minus the square of the xy second partial. So it looks like for this, it's what, minus 2x times minus 2x. That's not the usual situation, but it can happen, of course. And then the mixed partial is 2 minus 2y. And then d, positive, negative, 0 is, well, if it's negative, it's a saddle. If it's positive, you have to look at the xx second partial. So, and then that's kind of like Calc 1, where positive is a local min, negative is a local max. Okay, so it looks like when x and y are both 0, you get negative 4, so it's a saddle. 0, 2. Also, you get d is negative 4. So yeah, d is negative 4, d is negative 4 for those. For 1, 1, you're going to get, what, 4, which is positive. But then the xx second partial equals negative 2. And so this, sorry, is not for 0, 1. I'm doing this for 1, 1. And so that's a local max. And then minus 1, 1, you still get 4x squared minus 0. So yeah, this is d is 4. But then xx is positive 2. So that's local minimum. All right. Next one, find the absolute max and min of this function on the elliptical region. So if we had said 2x squared plus y squared equals 18, then you would only be doing Lagrange multipliers. But because of this less than or equal to, it's really the two-step process, where first you're looking for the gradient to be 0 inside 2x squared plus y squared less than 18. And then the second step is Lagrange on 2x squared plus y squared equals 18. Because the whole idea is that with this inequality, it looks like y goes from, so whatever, square root of 18, and then this is 3, so it's a little bit taller than it is wide, let's say. But yeah, with the inequality, we're basically looking at points on or inside this ellipse. And so you're going to use Lagrange on the boundary and look for critical points on the inside. So anyway, for this part, you're looking at 2x plus 2 equals 0, 2y equals 0. So we're putting minus 1, 0 on our list. As far as Lagrange goes on the boundary, it's 2x plus 2 is lambda 4x. 2y is lambda 2y. And then 2x squared plus y squared equals 18. So the second equation, I like to deal with the simplest, tells me that lambda is 1 or y is 0. If y is 0, the third equation tells me that x is plus or minus 3. If lambda is 1, the first equation tells me that 2x plus 2 is 4x. So that x is 1, and y is then, in the third equation, plus or minus 4. Cool. So the points I have to check are f of minus 1, 0, f of 3, 0, f of negative 3, 0, and then since f only depends on y squared, I will get the same thing at 1 plus minus 4. So at minus 1, 0, I get what? 1 plus 0 minus 2 is negative 1. At 3, 0, I get 9 plus 6 is 15. At minus 3, 0, I get 9 minus 6 is 3. And then at 1 plus minus 4, I get 1 plus 16 plus 2 is 19. So it looks like the minimum is minus 1, the maximum is 19. So I think the other wrong choices came from either forgetting about this inside step, right? Or missing these two possibilities here, being careless with that. But there we go. All right. Take a look at this next one. Find the maximum of this subject to this constraint. So this one was a little bit tricky with the reasoning. The thing to realize is, remember, closed bounded regions are the only types of regions that we're guaranteed to have both an absolute maximum and absolute minimum. If you remember back to Calc 1, if your interval goes on forever, you might not have either a max or a min, and you have things going like that. Things happen like that. So this problem here does not have an absolute maximum, because if you look at this constraint equation, that's a plane. It goes on forever. So for example, if like x and y are both 1,000,000, then z could be about what? Negative 1,000,000, and have this all work out. But if x, y, and z are all about 1,000,000 or negative 1,000,000, you know, x plus 4 squared is huge. Y plus 7 squared is huge. Z plus 9 squared is huge. We're adding 3 huge positive numbers together. So there is no maximum. So that was the intuitive idea, that it turns out we didn't phrase it this way, but we made you do several on the homework and I think on the quiz. This question is basically asking, find the point on this plane closest to the point -4, -7, -9. Remember, you could set up the distance formula to that, and the distance squared is exactly this f function that we gave you. So that was another way you, if you didn't want to think about this function itself, you might have been able to recognize it as the type of problem you saw on the homework a couple of times. So anyway, there is no maximum for this. And so let's see. So this, because it just has an equals, and we never did 3 variable unconstrained. I mean, this is Lagrange only. So we set up 2 times x plus 4 is lambda times 1. 2 times y plus 7 is lambda times 2. 2 times z plus 9 is lambda times 3. And then x plus 2y plus 3z equals 11. So if you solve for lambda in each of these equations, you can get that lambda is, what, 2x plus 8, and that's equal to y plus 7, and that's equal to 2/3 z plus 6. If you do the distribution, so you could figure out that what, y is 2x plus 1, that z is 3x plus 3. And if you shove those into the constraint equation, you get that x plus 2y plus 3z equals 11. So 5x, so 14x plus 2 plus 9. Am I doing this right? I don't remember what the answer is. So yeah, what, 5x plus 9x? Yeah, it seems right. And then 2 plus, yeah, so I guess x is 0 because we get 11 equals, plus 11 equals 11. So then y is 1 and z is 3. And so remember, that should presumably be the minimum then. So if x is 4, we get what, 16 plus 64 is 80 plus 144. Okay, yeah, this sounds familiar then, is 224. Again, if you weren't sure whether this was the maximum or the minimum, you could have just plugged in any other point on this equation. So like, for example, let's say, you know, that whole million minus a million thing, or recognizing the distance point to a plane. You know, if you weren't sure about that, you could have said, okay, I only get this one solution. Let me try another point that works. So for example, 11, 0, 0 works on this plane. And so you clearly get something that's bigger than 224, because as soon as you plug in the x, you get 225 plus 49 plus 81, which is clearly bigger than 224. So that could have also helped you figure out what was going on. So anyway, just another thought. But I guess let's get into integration. So this is the one where good old Canvas, it was bizarre. It was not letting us change this question. I don't know what was going on. So anyway, let's see here. D is the region in xy plane enclosed by y equals x squared minus 2. So y equals x squared minus 2 is what? Your y equals x squared parabola shifted down a little bit. And then y equals 1 minus 2x squared is, well, minus x squared shifted up. So, you know, that's 1. This is minus 2. And this region is what we're dealing with. You could do this dx dy, but then you'd have to split it into 2, because you see that which parabola, which your left curve changes, your right curve changes. So I think we'd prefer to do dy dx. But either way, we have to figure out these intersection points. So So x squared minus 2 equals 1 minus 2x squared gives us that 3x squared is 3, so x is plus minus 1. So I guess this is 1 minus 1, right? And then this is minus 1. Minus 1. The y values actually aren't important if we're doing dy dx. And so, yeah, we do x goes from minus 1 to 1. The bottom curve is x squared minus 2 equals y. And the top curve is 1 minus 2x squared, and then 2x squared y dy dx. So I get x squared y squared as my y antiderivative. At this stage, it's nothing too bad. What, this is going to be x squared times 1 minus 4x squared plus 4x to the fourth minus x to the fourth minus 4x squared plus 4. So I get integral minus 1 to 1. What is this? So I have a 5x to the fourth, so 5x to the sixth. Once I distribute that x squared, I have minus 4x squared minus negative 4x squared. That cancels. And then I have 1 minus 4 is negative 3, minus 3x squared dx. Anyway, this, you could do that this is an even function just to prevent some sloppy mistakes when you go in to plug in and subtract. But anyway, it looks like you get 2 times 5/7 minus 1. But this was supposed to be minus 8/7. I think I'm just going too fast here. Oh, yeah, because I screwed up this. This should have been 3x to the sixth. So this is 3. And then this is 3. So 3/7 minus 1 is minus 4/7 times 2 is minus 8/7. So yeah, just be a little careful. Don't go too fast like I did. Yeah, 4x to the fourth minus x to the fourth, of course, is 3x to the fourth, but then times x squared. Yeah. All right. Okay, so this one, we're stuck on this dx integration. So remember, you should really be mostly prepared to do substitution for this. So if I'm trying to do an x antiderivative, the only thing I could really try would be u equals x minus x squared over 2 pi. But then du is like 1 minus x over pi, which you don't have. So yeah, if I did u is x minus x squared over 2 pi, the du is 1 minus x over pi dx, which I don't have. I have this 2 over pi squared y. So I'm stuck with the dx, which, remember, then you're supposed to take the hint. Like, should I try polar? Should I try switching the order? And so switching the order is what you should do for this. So we should try dy dx. So the dx dy picture you have to decode. So it's telling us that x equals y squared over pi. So something like a parabola, x equals y squared over pi, is the right curve. And then x equals 0 is the left curve. Because remember, that's what these bounds are telling us. And then hopefully this intersection happens at y equals pi, and we're dealing with this region that's both type 1 and type 2. So it could be some weird trapezoid-like shape with a curved side if this intersection doesn't work out. But you can, in fact, confirm that that when y equals pi, we're on, oh, well, I guess no matter what, this is going to be pi. And then if y is pi, x ends up being pi as well. Okay. So that means then when we go to do it dy dx, our bottom curve is, well, we have to solve for y, so y is the square root of pi times x, and then y equals pi is the top. So it would be 0 to pi, square root of pi x to pi, and then 2 over pi squared y cosine x minus x squared over 2 pi dy dx. So we're not sure that this is actually going to work yet, but we do know that we can at least get started on the y antiderivative, because this will then be, well, y squared over pi squared cosine of x minus x squared over 2 pi between y equals pi and y equals square root of pi times x. Right? So it's 2y times a bunch of things we're pretending are numbers with respect to y. And so then you get integral 0 to pi of 1 minus x. Yeah. When you go through and do this, 1 minus x over pi times cosine of x minus x squared over 2 pi dx. Right? Because pi squared over pi squared will give me this 1, and then pi x over pi squared gives me x over pi. And notice that was exactly what I was missing for this substitution, which then I can apply here to basically get that this is what? Cosine u du. So sine u between 0 and pi. So pi minus pi squared over 2 pi is pi minus pi over 2, which is pi over 2, which is 1. And then sine of 0 is 0. So looks like I get 1. So again, anytime you see some kind of complicated inside function and you don't seem to have what you need to make the substitution work out, that's what you get. All right. So let D be the region in the first quadrant of the xy plane bounded by y equals 0, y equals x, and these circles, which iterated integral is equal to this. So this sounds like a polar type situation. We have y equals 0, y equals x. We have a circle of radius 1, a circle of radius 2. And so putting it all together, this seems to be the region that we're looking at. We know that y equals x is at an angle of pi over 4, and y equals 0 is at an angle of theta equals 0. And then r is between 1 and 2. So we can immediately get rid of that. So yeah, you don't want to do this dy dx because notice if you do dy dx, sometimes the bottom curve is the smaller circle, sometimes the bottom and top curve are the lines, and sometimes the top curve is the bigger circle. So if you did dy dx, you'd actually have to split it into 3 pieces. And so you don't want to have to do that. And so anyway, yeah, it looks like if you wanted to draw this region for y between 1 and 2, x between 1 and 2, y starts at 0, it stops at that circle. You know, the region for which that is the dy dx bounds looks a little bit more like that, right? It kind of goes up more like that. So anyway, yeah, that's not the right region. So anyway, polar, looks like the bounds are good for all 3 of these. Then you just have to make sure to use that this is what? R squared minus R cosine theta e to the R squared sine squared theta. Because remember, x is R cosine theta, y is R sine theta, so x squared plus y squared is R squared. But then the last little detail is that dA has your extra factor of R. So that's the correct answer. And so again, we know that this choice versus this choice are very, very close, but it's up to you to look at all of them and notice that, wait, those are almost the same exact answer. What's the difference? Oh, one has the R, one doesn't have the R, so we have to be careful, make sure we have the R. Uh-oh, I guess I didn't let this go before I hit print before it all loaded. So let me pull this up. Okay, so this is the disk of radius 2. So mass is, of course, the double integral of density. And so we actually had you calculate what the mass is. And there is a nice little shortcut because this disk of radius 2 is odd with respect to, well, I'm sorry, it's symmetric over the y-axis and it's symmetric over the y-axis. And this term here is odd with respect to y. This term here is odd with respect to x. So when you go through, you could do the double integral of 10 plus the double integral of x plus the double integral of y. But because of the symmetry of the region and the odd symmetry of the function y, that integrates to 0. Similarly, that integrates to 0. And so for the mass, you just get 10 times the area, which is then pi times 2 squared because it's a disk, so 40 pi is your mass. Again, if you're not comfortable with this odd symmetry and things like that, if you switch to polar, you'd be doing the integral from 0 to 2 pi of cosine theta. Well, cosine theta has a periodic antiderivative, so when you plug in 0 and 2 pi, you end up getting 0. same thing for this term with y, you'd have sine of theta integrated 0 to 2 pi, which ends up being 0. So anyway, mass was 40 pi. And then for x bar, you do 1 over the mass times the same double integral, but times an extra x. And we didn't have you evaluate this. You know, we didn't want there to be too many steps in the calculation, but 10x is odd with respect to x. This region is symmetric over the y-axis, so that goes away. Same thing for that, and so the answer choice for this, I believe we left it as, 1 over 40 pi, double integral. Oh, so I did convert it to polar, but x squared is going to be r squared cosine squared theta, r d theta dr, and then I think 0, 2, 0, 2 pi as far as the bounds go. And same thing, y bar is 1 over the mass times the same integral, but with an additional factor of y. Well, 10y is odd with respect to y. xy, you could use x or y. Again, it's not important. If you have both, if there's two reasons that something is 0, you know, it's still 0, right? And so anyway, you end up getting ends up being equal, but it's going to be r squared sine squared theta r d theta dr. So don't forget those. Well, I think the only two of them had the correct mass, and then the wrong choices forgot these 1 over 40 pi's. So don't forget that. All right. What's this next one? Next one is just a triple integral. So basically you're supposed to do xy squared over z dv, where e is given by z is between 1 and 2, x is between 0 and y squared, and y is between 0 and 2. So basically, as soon as you see that the x bounds depend on y, you're going to have to be careful to put x inside of y. Nothing else really matters here. So I'll just do x on the inside. So z 1 to 2, y goes 0 to 2, and then x goes 0 to y squared. And so then you just kind of go through step by step. So the x antiderivative is x squared y squared over 2z between 0 and y squared. So I end up getting y squared squared is y to the 6th over 2z. And so at this stage you can separate it, but what? The y antiderivative is y to the 7th over 14z between 0 and 2 for y, which ends up being what? 128 over 14 is 64 sevenths. So 64 sevenths, natural log z between 1 and 2 is 64 sevenths, natural log 2. All right. And then finally, set up an integral that gives the volume below the plane z equals 10 minus x minus y, and above the triangle with vertices. So I did specify in the xy plane, but you can pretty clearly see that that's the case here. So there's two ways we talked about volumes. There's, for volume, it could either do a double integral at the volume below z equals f of xy and above the xy plane is a double integral of f of xy. Or you could do the volume of a solid E is just the triple integral of the boring constant integrand 1 times dv. And so, again, if I have the triple integral of an interesting function, this is the mass of a solid with density F. And so that, I think, was one of the more common wrong answers. Was one of the triple integrals that we gave was, or one of the wrong choices was the triple integral of 10 minus x minus y. That would represent the mass of an object with density 10 minus x minus y. Okay, so instead, the correct answer was a double integral. Yeah, because there were two choices of triple integrals. They both had 10 minus x minus y as the integrand, so those are both wrong. And so then it's all about getting the bounds right. So we have to visualize our xy situation. And the triangle that we're above is type 2, but not type 1. So notice the top curve changes, so you can't do it with one dy dx. You have to do it dx dy if you want to do it in one piece. And so if you figure out the equations of these left and right lines, you end up getting that for y between 0 and 1, x starts at y, it stops at 2 minus y. So one of the other wrong choices was we did sort of a bogus dy dx situation. Which is bad because the top curve changes. And so therefore, this region's not type 1. You can't do it in a single dy dx situation. That basically, when I write this, I'm saying that x is the bottom curve, 2 minus x is the top. But that doesn't make sense because those two intersect at x equals 1. And so it's just bogus. So not good. Make sure you're careful about that. So anyway, that's the exam. And I'll see you later. So let me know if you have any other questions on that, but hopefully that clears up some things.